And today we continue talking about multiplication rule. Today's class, I'm going to start with the definition of conditional probability. P of A given B is a conditional probability. It is a probability, but the probability has a condition. So we call this probability a conditional probability. Then what's the condition of the probability? The condition is right here, is behind the bar. We have a vertical bar. We call this notation, how do we say this notation? We call this notation the probability of A occurring given B already occurred. We can call this P of A given B. Given, whatever following given, that's the condition. In other words, we assume event B already occurred. We assume event B already occurred. Then under that condition, we consider the probability of A occurring. That is a conditional probability. I think the best way to understand the definition is look at an example. Let's consider this classical probability model, rolling a die. We should be very familiar with this example by now. Rolling a die. The sample space, 1, 2, 3, 4, 5, 6. We roll a die and observe the number from the die. Then the sample space contains all the possible 6 outcomes, number 1 through 6. We consider two events, A and B. A is the event. We roll in a number 6. We roll a number 6. B is the event. We roll an even number. We roll an even number. Now we are going to consider the two probabilities, the following two probabilities, P of A and P of A given B. P of A is just a probability. There's no condition attached to the probability. It's just a probability. And this probability has a condition. The condition is B already occurred. So let's see the value of the two probabilities. Firstly, P of A. We roll a die once. All the possible outcomes are 1, 2, 3, 4, 5, 6. And what's the probability that we roll a number 6? It's classical. So the probability is a fraction with the denominator equal to 6, the total number of outcomes in the sample space, with the numerator 1, because among the 6 outcomes in the sample space, only this outcome favor the event occurring. So one outcome favor the event occurring, so 1 over 6. So we know this, right? Yeah, getting a number 6, the result, the probability is 1 over 6. And now we consider this conditional probability, P of A given B. Knowing the conditional probability is still the probability of A. It's just we have a condition attached. The condition is B is already occurred. So let's consider that. Let's consider. Assume B already occurred. What is B? B is we roll a die and we get an even number. So we already know the number we get is an even number. Under that condition, what's the chance to get a number 6? So that's what this conditional probability is describing, right? The probability of A given B already occurred is the probability we get a number 6. Suppose we already know the number is even. We already know the number is even, then in the sample space, we of course will not consider 1, 3, and 5, right? So when we have a condition attached, the original sample space actually does not apply. We actually have a shrunk or restricted sample space. Restricted sample space is smaller, so it's a shrunk sample space. Since we already know B occurred, we already know the number is even. Of course, we will not consider 1 or 3 or 5, right? We would only consider 2, 4, or 6. And among 2, 4, or 6, the chance of getting number 6 is 1/3. Do you see that? Does that make sense? A conditional probability is different. It has a condition attached. Because the condition that is attached, the sample space shrunk to a restricted version. Just like this example, since we already know the number is an even number, we of course will not consider 1 or 3 or 5. We would only consider 2 or 4 or 6. Among those 3 outcomes, we have the chance of getting number 6 is 1/3, right? So it's different, right? Okay, perfect. Thank you, Ashlyn. Oh, thank you, Chloe. I would have to remember to do that later, but not big deal. Yeah, as you can see, P of A given B is different. This one has no condition, this one has a condition. When the probability is a conditional probability, when the condition is attached, we normally, we should always have a restricted sample space. So finding the value of a conditional probability, the key is to know the restricted sample space and then use either classical model or empirical model, then you can just find the probability as always, right? Okay, so that's the definition. That's the definition of a conditional probability. Now please look at those two, look at these two notation, P of A given B and then P of B given A. They look similar, right? Yes, they are both conditional probabilities. However, they are definitely not equal. They are definitely not equal. The one on the left, this is the probability of A. A is the main rule. Probability of A, that's the event. Suppose or given B already occurred. And this one is the probability of B, given A already occurred. Well, maybe we can still use, I think we still can use this example to see the difference between the two probabilities. And we already know P of A given B is 1/3, right? Suppose we already know the number is even. What's the chance of getting a number 6? 1/3. Now what about P of B given A? The probability of B given A has already occurred. The probability of getting an even number, suppose we already know the number is 6. A is getting a number 6, B is getting an even number. And what's the chance of getting an even number given the number we roll is number 6? Yeah, think about that and let me know. What do you think? We already know we got a number 6. And what's the chance we get an uneven number? What's the chance of getting an uneven number? Yes, exactly. Perfect. It is 100%. We already know is a 6. 6 is even, right? Perfect. And those two, as you can see, they are different, right? They are different. In general, those two represent two different conditional probability. All right, with the definition of conditional probability understood, we can cover the other formula in the multiplication rule. Let's recall what is the multiplication rule. We have learned the addition rule last time, right? We learned the addition rule, and we know we use addition rule to find the probability involving OR. And the multiplication rule is to find the probability involving A and D. If we need to find the probability involving and first thing we need to do is to consider or determine is the two events. Let's say we need to find the probability of A and B. First thing we need to consider is to determine if AB dependent or independent. Yeah, INDEP means independent. If AB independent, then P of A and B is P of A times P of B. Find the probability for each of the two events and multiply them together. Multiplication rule, right? So multiplication is the operation we need to apply when we apply the rule. And what if this chart is a little bit, let me make the looks better. Maybe longer. And this is AB independent. This is AB dependent. If it's AB independent, the formula we're going to use is just multiply them together. Suppose AB dependent, then P of A and B would be equal to P of A times P of B given A. Or P of B times P of A given B. It really depends on which event occurred the first time. Well, you don't have to struggle with this formula because it doesn't look like complicated. We are going to learn that formula by using it. Yes, we are going to learn how to use that formula by using it. So let's consider an example, another example. The setting of the example. How about 4 of them? Okay, 4 of them. Same size. 6. Okay, the setting of the example is we have a box, or a bag, black bag. We cannot see what's inside the bag. And in the bag, in fact, in the bag, we have 10 marbles. 10 marbles with the same size. So it means we don't know the color unless we see it. But they are in the bag, we don't really see them. We know there are 10 marbles. And there are 4 red marbles, 6 black marbles. That's the setting in the problem. And we consider 2 cases, okay? The first case, okay, we consider 2 cases. The first case is with replacement. The second case is without replacement. Okay. We are going to find the probability. How about we're going to find the probability of E? What is E? E is the probability is the event we are trying to find the probability is the first time we got a red color, and second time also get a red color. How about that? We want to find the R1 and R2. Okay. Find probability of R1 and R2 in the 2 cases. Let me explain what is R1 and R2. R1, so you have a bag. You have bag. The experiment we are going to apply, the experiment we are going to conduct is we draw 2 marbles from the bag. So we're gonna do that with 2 steps. The first step, we stick your hand in the bag and you mix them so you don't know which color is which color. So you just randomly pick a marble and record a color. Okay, in the first case, you put the back because with replacement. And then you mix them, you mix the 10 marbles, and then you get another one. And then you record the color of the second marble. So that is case 1. That's the experiment for case 1. You draw 2 marbles in succession. I think it's important for me to write it down. So draw 2 marbles randomly, of course, in succession. All right. So first case, you draw a marble, record the color, and then put it back, and then you get another one, record the color, and then put it back. So that is with the replacement. And then case 2 is you grab a marble and you record the color, and then you do not put it back. Case 2 is without replacement. So in the second case, you do not put it back, you throw it away. Then knowing before you go ahead to take the second marble, in the bag, there's only 9 marbles left. Okay, and then you draw 1 from the 9 marbles and then record the color and then throw it away. Do you see what's going on in the setting of the problem? Yeah, let me repeat it. It's a lot going on. We have a bag. In the bag, we have 10 marbles with the same size. They are marbles, so they are all spheres, right? Same shape. Among the 10 marbles, 4 red colors, 6 black colors. And we are going to do this experiment. We are going to draw 2 marbles, TW, draw 2 marbles in succession. And we are going to consider this probability under 2 different situations. The first situation, the first case, with replacement, is we grab a marble, record the color, and then put the marble back into the bag. So when we need to take the second marble in the bag, we still have 10 marbles. That's the first case, with the replacement. Second case is without replacement. We get a marble, we record the color, and then throw it away. Do not put it back. Do not put it back. So when we take the second marble, we only have 9 marbles left in the bag. That's the difference between the 2 cases. We are going to find the probability of this event in the 2 different cases. What event? The probability involves A and D. We want to know the probability of the first time get a red marble and the second time get a red marble as well. R represents red, R-E-D, okay? R means red. All right, so let's get started. Case 1. Solution. Case 1. Case 1 with replacement. Please consider, in the first case, when we draw the 2 marbles with replacement, do R1 and R2 dependent and independent? That would be always the first thing to determine when we need to find the probability of an event involving A and D, right? Are they dependent or independent? Think about it. Means the first time we got a red marble, or not get a red marble, would that change or affect the chance of the second time getting a red marble? Would R1 in any sense, any way, affect R2? Independent. Actually, this case 1 is independent. Case 1 is independent. Because you draw a marble and then you record a color and then you put it back. So when you draw the second marble, you still have the same setting. Still 10 marbles, 4 red colors, 6 black colors. So the first time the marble is black or red, it doesn't matter, does not affect the chance of getting a red marble the second time. Can you feel that? Yeah, would you consider that again? Okay, perfect. So we agree. Let me write it down. You need to memorize, understand and memorize with replacement. With replacement. With replacement. It means you put it back, right? Everything, all the settings are recovered. Is independent. Independent, okay? With replacement is independent. So when the two events are independent, how do we find the probability of R1 and R2? When the two events are independent, the probability of R1 and R2 is P of R1 times P of R2. What's the probability of R1? What's the probability you draw a marble from the 10 and the marble is a red color? We have 10 marbles, right? And what's the chance getting the red color? 4 of them are red, so 4 over 10. It's a very simple classical, right? Yeah, we in total have 10 marbles, 4 of them are red color, so the chance of getting a red marble, 4 over 10, very easy, very simple. And what's the probability that second time get a red marble? It's gonna be the same thing, okay? Because with replacement, whatever you get the first time, you put it back. Yeah, you got a red color, you put it back. And when you take the second marble in the bag, we still have 10 marbles with 4 red color, 6 black color. So 4 over 10 again, right? Do you agree, guys? Very good. Yeah. It is independent. It is independent. When is independent, perfect. Thank you guys for your response. So when in a case with replacement, the probability of getting 2 red colors is 4 over 25. All right, 4 over 25. And now let's look at case 2. Now let's look at case 2. This is case 1. Case number 2. Case number 2 is without replacement. All right. And we want to find the probability of R1 and R2. Since the probability involves A and D, we need to know, are the two events dependent or independent in this case? Would the first time getting red color or not getting red color affect in any way the chance of getting a red color the second time? Knowing we are considering the second case without replacement means whatever you get the first time, you throw it away. You do not put it back. So when the second time you need to draw a marble, you're gonna pick one from the 9 remaining marbles, right? Yeah, you don't have 10 marbles to pick from anymore. You only have 9 marbles left. If the first time you get a red color and you record a color and you throw it away, then before you draw the second marble, you have 9 marbles left in the bag. 3 of them are red, 6 of them are black. You see what happened? So suppose the first time you get a black marble, then you throw it away. Then right before you draw the second marble, you have 9 marbles left in the bag. 4 of them are red, 5 of them are black. What do you think? Would the first draw in any way affect the chance of getting a red color the second time? Would R1 affect R2? Would R1 affect R2? You really have to see it, guys. Would the first time you get a red marble affect the second chance, the chance of getting a red marble the second time? Yeah, of course. Yeah, thank you, Ashton. It will, right? Like we have questions like a donut in Pearson. Let's say there are donuts, and the red color is your favorite color, favorite flavor, and then the first person take away one red donut, and you have less. You definitely have less chance to have a donut because there was 4. Now there's only 3 left, right? So obviously the first time getting red marble will affect the chance of getting a red marble the second time, because in case 2 we are doing without replacement. So the two events are dependent. So let me write it down. This is very, very important. Very, very important. Without replacement, independent. Without replacement. Did I say something wrong? I'm sorry. Without replacement, dependent. I apologize if I misspoke anything. Dependent. Yeah. Put it together. With replacement, independent. Without replacement, dependent. Let it settle with you, okay? Yeah, think about, try to make sense of why. Consider the example we are looking at now. With replacement, independent. Without the replacement, dependent. All right, so let's see how do we find the probability when R1 and R2 dependent. This is new, okay? This is new for today. R1 occurs first, right? Okay, so let's let R1 occur first. And then when we draw R2, when we draw the second marble, that's gonna be under the condition that the first marble is red. So this is P of R1 times P of R2 given R1. R1 occurs first, happens first. R2 happens the second, but R2 happens under the condition that R1 already occurred. But you don't have to struggle with the notation here. I would recommend you consider this is a multiplication rule, so you are definitely using a multiplication operation. And then you want to think about fundamental counting principle. In essence, behind this formula actually is a fundamental counting principle for the classical case. So let's think about to draw 2 marbles in succession. We have 2 steps, right? The first step is to draw a marble. Yeah. So R1 and R2. The first time we draw R1, what's the chance the first time we get a red marble? We have 10 marbles. We have 10 marbles. Among the 10 marbles, we have 4 red color. So the probability of getting a red marble the first time is 4/10. Multiply, since we are using multiplication rule, right? Multiply the probability of the second time also get a red marble. You don't have to worry about the formula. You do not need to really write this. Just think about multiplication rule and the fundamental counting principle. After that, we're going to find the probability getting the second marble red. So since the first time you already get rid of a red marble, now in the bag you only have 9 marbles, right? How many of them are red color? How many of them are red color? The first time getting the first time 4 minus, yeah, exactly 3. Perfect. I think it's pretty clear. If it's not, please let me know. Does that make sense? The only difference is this part. That's the probability of the second time get a redder marble. In the case with replacement, when we get a second marble, we still choose one from the 10 marbles available. Among the 10 marbles, we still have 4 red color. So the probability of second time getting red marble is 4/10. But in the case of without replacement, the chance of getting a red marble the second time really depends on what we get the first time, right? Firstly, the total number of marbles reduced to 9. And since the first time we get a red marble, because we are considering getting 2 red marbles, the first time I already get a red marble, so the number of red marbles reduced by 1 as well, so 3/9. And then we calculate, we multiply the two probabilities together. So we have 2/5 times 1/3, that is 2/15. Do you understand? You make sense? Okay. Yes, makes sense. Very good. Okay, so let's look at some related similar problem and practice. This time we mainly practice dependent case. We did the independent case last time. Please watch the video if you missed it, that class. You want a free trip to Madrid, Spain, and can take 2 people with you. All expenses paid. 10 of your friends are begging you to take them. You write each friend's name on a card, place the cards in a hat, and select one name. Then you select a second name without the replacement. Okay, this is a very important information. Without placing back. So this is without replacement. We know without replacement, the 2 events are going to be dependent, right? Going to be dependent. Without placing the first card, if 3 of your 10 friends speak Spanish, find the probability of selecting 2 Spanish-speaking friends. Okay, let's sort the settings here. How many friends? 10 friends. 10 friends. Among the 10 friends, 3 is Spanish speaker. The other 7, non-speaker, non-Spanish speaker. All right. Instead of red marble, black marble, here is Spanish speakers, non-Spanish speakers. It's really just similar. Okay. So we are looking for the probability that both the friends that you selected are speakers. How about S1 and S2? Whatever the level you feel comfortable and you understand, makes sense to you. S1 would be the first time you pick a name and that friend is a Spanish speaker. S2 would be the second time you pick a card on which the name belongs to a friend who speaks Spanish. S1 and S2 are dependent, right? We agree? Dependent. Similar idea with the marble example. And we do the S1 first. What's the probability the first time we get a Spanish speaker? 10 friends. From the 10 cards, you draw 1, and that happened to be a Spanish speaker. That means that one person is from the 3 Spanish speaking friends, right? So 3/10 is the probability of S of 1. 3/10 is the probability that first time we get a Spanish speaking friend. and then multiply the second time, we get a Spanish-speaking friend as well. Yeah, the second time we get a Spanish-speaking friend. But this time, your sample space shrunk. You do not have 10 cars in the hat anymore. You only have 9 cars left because you did it without replacement. That makes sense. If you already choose it, what if you pick both of the same person? Then it doesn't work, right? So it has to be without replacement. So when you pick the second friend, you are picking from the remaining 9 friends. Among the remaining 9 friends, how many of them speak Spanish? We know the first time you already got a Spanish-speaking friend. Okay? The first time you get a card on which the name belongs to a friend who speaks Spanish, you already got a Spanish-speaking friend. When you draw the second card, you only have 9 cards left. And how many Spanish speakers in that 9 cards? Take your time. 2. Awesome. Yes, it is 2. Thank you, Jack. Thank you, Jennifer. Very good. Only 2 left. There we go. That's it. Right? And then we do, it's better we know some skills, simplify fractions. If not, just depend on the calculator. I'm fine with that. 2 over 10 is 1 over 5. 3 over 9 is 1 over 3. So the result is 1 over 15. The probability is 1 over 15. All right, without replacement, dependent. Let's continue. So literally, you don't really need to remember the formula. You just need to know the second probability is going to be a conditional probability. When you find that probability, the situation, the setting has changed. The sample space shrunk, and the outcomes in the sample space also changed. Like this time, you don't have 3 Spanish speakers anymore. You only have 2 left. Okay. Let's see. Let's try this one. You are dealt 1 card from a 52 card deck. Part A. Find the probability of getting a heart, given that the card you were dealt is a red card. All right. We are looking for a conditional probability. So this one is not is not about applying the multiplication rule in the dependent case. This problem is to find conditional probability. Part A, we need to find the probability of getting a heart, comma, given that the card you were dealt is a red card. That means the probability has a condition attached. It is a conditional probability. So let's see, how do we do that? So we find the probability of getting a heart given the card you draw is a red color. Okay, so with the red color condition attached, the sample space is not going to be the 52 cards anymore. The sample space go from 52 cards to a restricted sample space, all red cards. How many red cards? Half of them, 26 red cards. 26 red cards. So that is the new sample space. That's the restricted sample space. Among the 26 red cards, how many of them are heart? The 26 red cards has 13 hearts, 13 diamonds. So 13 and a half, right? Is that understandable? Okay, awesome. Part B, find the probability getting a red card given that you were dealt a heart. So this time we are looking for probability of getting a red card given a heart. Just switch the location of the two events, right? So let's see now what's the restricted sample space. The sample space will shrunk to, because we already know we got a heart. So the 13 heart cards, right? So the denominator is 13. Among the 13 heart cards, among the 13 heart cards, how many of them are red? They all are red. So 1, right? This is similar with a question I explained earlier on the note. On my OneNote, is when you switch the two events, they are different, right? They're different. See this one. Okay, this is a good one. This is empirical. Okay. So how do we find the value of a conditional probability when the model is empirical? So let's see this problem. Driver survived, driver died, were with a seatbelt, without a seatbelt, right? So that's the table, total. A, find the probability of not surviving a car accident. So find the probability of died. Not surviving means died, right? Not surviving a car accident. Given that the driver did not wear a seatbelt, no belt. Okay? So the original, we consider all the subjects, that is 577,006, right? But now we already know the subject did not wear a seatbelt. We already know the subject did not wear a seatbelt. So we are not going to consider this much subjects anymore. We are going to consider those people who did not wear seatbelt, right? So that's going to be our denominator. Well, you can still can see that as the sample space shrunk. With the condition, the sample space right now is 164,128. Among those people who did not wear a seatbelt, how many of them died? This many people died, right? 1601. And then you do the division, find the result. I'm going to leave the calculation for you. So that's part A. Part B. Find the probability of not wearing a seatbelt given a driver did not survive a car accident. This time, we're going to switch the two events. So we are looking for the probability no seatbelt given the person died. And we want to know among the people who already died, how many of them didn't have a seatbelt? You know, the two probability gives you different meanings, right? Help you to interpret the different situations is pretty important. Let's see how many people died. People died. So we would not consider 577,000 as the denominator, because those people have some of them didn't die, right? So we're gonna consider only the people who died in the accident. Among the people who died in the accident, 2111. How many of them did not wear a seatbelt? Drivers died. This many did not wear a seatbelt, right? 1601. You know, I actually want to know the probability. Let's find out. One 601 divided by 164,128. How about let me round it to, how about let me write it as a percentage. So this is gonna be 0.98%. 0.98%. Like less than 1%, right? Less than 1%. And this one, do I have two of that? So this one we're gonna divide 1,601 by 2,111 and times 100, so it's gonna have about 76%. 76%. Right? So among the people who did not survive an accident, the 76% of them did not have a seatbelt. So you can actually use this result to make a point, right? You can make a point. Like wearing seatbelt is very important. And this one, among the people who did not wear seatbelt, drivers, no seatbelt, and this many people died, right? Well, even is a low percentage, but still like a shy 1%, almost 1%, almost 1% every 100 people, right? Every 100 people do not wear seatbelt while driving, and one of them died. That's still very significant because the consequence is very severe. Do you guys have any questions about this problem? Finding conditional probabilities. Okay, very good. And let me check. So I'm gonna go back 11.6 because we have a concept did not cover last time. I like the order I'm doing now. I don't really like the order on the textbook. I like to teach complement rule and then addition rule and then multiplication rule and then do the odds. So we are going to talk about odds as the last part of the 11.6 and 11.7. What is odds? Let's say A is an event, okay? A is an event of an experiment. P of A is the probability of A occurring. P of A prime, which is 1 minus P of A, is the chance of A not occurring, right? Then we call P over A over P over A prime as the odds favoring A occurring. And then we call P of A prime over P of A as the odds against A occurring. When I wrote the definition, I wrote the odds as a fraction. But in fact, the fraction is a ratio. Odds is a ratio, okay? Odds actually is a ratio. This can be written as P of A to P of A prime. Is actually a ratio. Like if you bake or your mom bake, you might know what is the ratio. For example, if you want to make a cake, you put 1 cup of flour with how many cup of water? Let's say if you put 1 cup of flour and 1.5 cup of water, you make a dough, right? So the ratio of the flour and the water be 1:2. This is called 2, the colon 1 to 1.5. And odds is a ratio. Odds is a ratio. The ratio of the chance of A and of A occurring and the chance of A not occurring. So P of A to P of A prime. And the odds against would be P of A prime to P of A. For example, a simple example, rolling a die. Let's say the rule of the game is you win if you get the number 6, right? So let's say A is getting number 6. Then P of A would be 1 over 6, we know that. Then the complement would have chance 5 or 6. Not winning would be 5 or 6, right? Then the odds winning means favoring, the odds favor A occurring is also called the odds of winning, would be this probability to the probability of the complement, which is 1 to 5. We can get rid of the 6 because the denominator is the same thing. So 1 to 5. With the odds found, the people who actually work are active in a casino, they use the concept of odds more than probability, because they can see if I play the game, my chance of winning, I can see from the odds, I know the chance of winning, and my chance of losing, I can see the, you know, the comparison together, right? So the odds of winning in this simple game is 1 to 5. Is 1 to 5. That means I have 5 times chance. The chance of losing is 5 times bigger than the chance of winning. Do you see what I'm talking about? Or the chance of winning is only 1/5 of the chance of losing. Yeah, some people they like to use the odds. And of course, the odds against A occurring, or you can see that as the odds of losing, would be 5 over 6 to 1 over 6. That is 5 to 1. Okay, what's the odds of losing? The odds of losing 5 to 1 means the chance of losing is 5 times more than the chance of winning. Right? Does that make some sense? Am I clear about the definition of odds? Odds favoring event A occurring, odds against event A occurring. Odds is a ratio, and we have different ways to express the ratio. We can do like this, you know, a number, is that colon? Yeah, colon or some, this colon and another number, so ratio. Or we actually can use a division to do the ratio, right? You can put a P of A on the top, P of A prime on the bottom. Depends on the problem. We need to understand the concept first. Okay, perfect. We understand the concept first and then we practice. Let's practice coach. We covered those already last time. Is this about the ratio, about the odds? No. Yeah, this is about odds. Okay, this one should be about odds. Number 6. One card is randomly selected from a deck. Find the odds in favor of drawing a picture card. Okay, so let's use A to represent drawing a picture card. All right, then P of A equals 3 over 13. Do you agree? Do you agree? You can think about the sample space as 1, 2, 3, all the way to 13, right? You can see the experiment as draw a card from the deck and observe the number. If the number is from 1 through 10, no picture card. If the number is from 11 to 13, then the card is a picture card. Among the 13 numbers, 11, 12, 13, they are picture cards, so 3 over 13. 3 over 13 is the probability of A. Then the probability of A prime would be 10 over 13, right? Yeah, the two probabilities must add up to 1. Then what's the odds favor A occurring? The odds favor A occurring would be P of A to P of A prime, which is 3 over 13 to 10 over 13, which is 3 over 10, 3 to 10, 3 to 10. Means the chance of winning, let's say if you draw a picture card is winning, the chance of winning 3, the chance of losing 10. So you can compare the chance of losing with the chance of winning with the chance of losing. Okay? Does that make sense? Okay, very good. Part B. Part B is to find the odds in favor of drawing a black card. Well, since this time the event only consider color, then I can modify my experiment and choose this set as my sample space. My experiment would be draw a card from the deck and observe the color. My experiment, this case, is draw a card from the deck and observe the color of the card I drew. It's either red or black, so the sample space is black and red, equal probable. So the sample space is very simple. That makes the finding probability is very easy. Chance of getting a black card, half. Chance of not black card, half, right? So the odds favor getting a black card equal to P of B to P of B prime, which is a half to half, 1 to 1. The odds of getting a black card is 1 to 1. Like the chance of getting a black card and the chance of not getting a black card is the same. Yeah, some people think differently. To me, because I did the probability before I know a little bit about casino, so I like probability. But for people, they are very has been very active in the casino, and they didn't really take the probability classes. They understand the odds better. In practice, people use odds a lot. I can see why, because they can compare the chance of winning with the chance of losing. Then they can make a decision, play or not play, right? Okay. So you basically take the numerators. You are right, that's a very good question. I only take the numerators if the two fractions have the same denominators. If they do not have the same denominators, they should have, because they are under the same classical model or whatever the model. So they should have the same denominators. If they have the same denominators, you can get rid of it, all right? And you also want to simplify. What if you have, let's say, if it happens to be 2 over 6 and the other one is 4 over 6, How do you simplify this ratio? And you get rid of the 6 denominators, the same thing, right? If they have the same denominators, you can get rid of both. And then 2 to 4, 2 to 4 is not simplified. 1 to 2 is simplified, okay? 2 to 4 is not simplified. 1 to 2 is simplified. Divide by 2, divide 2 by 2, divide 4 by 2. And basically, it is a, you can also understand that as division of fractions. Let's say 2 over 6 to 4 over 6. You basically can write that as 2 over 6 divided by 4 over 6, right? And remember, when we divide fractions, we use a keep change flip. We keep 2 over 6, change division to multiplication, and then flip this fraction 6 over 4. And they cancel. 6 cancel 6. 2 over 4 can be reduced as 1 over 2. So 1 over 2 can be written as 1 to 2. Hope that helps a little bit. Actually, does that make a little bit sense? Okay, very good. That's a very good question, by the way. We have one more part, part C. This time, we are looking for the odds against drawing a red jack. Since the event involved has a color considered, has the, the number jack is 11, right? Considered the sample space has to be the 52 cards. We can't take a shortcut. So the sample space is 52 cards. And the probability getting a red jack, okay? I think there's 2 red jacks. There are only 2 red jacks. In total, we have 4 jacks. Half of them are red, half of them are black. So 2 red jacks among the 52 cards. Yeah, we can reduce this fraction to 1 over 26. Then the chance of not getting red jack would be 25 over 26, right? The 2 probabilities must add up to 1. Then the odds against getting a red jack would be, since it's against, since it's against, we have to do the not happening first. The probability of red jack not happening, we need to do that first. Be very careful the order. That's the only difference between odds favor and odds against. So 25 over 26 is 2, 1 over 26. In this case, the denominator is same, then we can get rid of them. So 25 to 1. Yeah. So if you wanna, if in this case get a red jack is a success, means winning, then the chance of losing is 25 times more than the chance of winning. And you can see the comparison. You can compare the chance of losing with the chance of winning, right? This sounds good, everybody? Okay, let me sort what we have learned in this in 11.6 and 11.7. I kind of like change the order of the content. We did cover the complement rule, like P of A plus P of A prime is 1. A prime is a complement of A, means A not occurring. We covered that. We also covered addition rule. We use addition rule to find the probability of A or B. When we need to find the probability of A or B, we determine if the 2 events disjoint or not. If the 2 events are disjoint, if A, B disjoint, then P of A or B is P of A plus P of B. In the case the two events are not disjoint, P of A or B is P of A plus P of B minus P of A and B. And I give you a structure and I shown you how to apply it, right? So you're gonna write that structure in your scratch paper and find the numbers, put in the cells. So we cover that addition rule. For multiplication rule, we also did P. Multiplication rule is to find the probability of P and B. I'm gonna use I'm going to take this down. If A and B are independent, then P of A and B is P of A times P of B. If A and B are dependent, suppose A occurs first, then the probability of A and B is P of A times P of B given A, knowing this probability is going to be a conditional probability. And we also covered odds. I think we covered a lot, but I don't mind to do a little bit more about at least one. Okay? I'm going to find an example about at least one. We did this part, at least one. So only one questions? Okay, how about let's go to Pearson. Let's go to Pearson, practice a little there. Majority of the participants from the essential class anyway, so don't mind started earlier. (11.6). This one. We have some questions skipped last time because, for example, the odds problem, right? Let's see if this is about odds. Yeah, it is. If the odds in favor of event A are A to B, then the probability of the event P of E is given by the formula. Okay, so this problem actually is a challenging problem. I'm going to explain this problem on a scratch paper, on a note. This actually takes a little bit algebra skill. P of E plus P of E prime is 1, right? So P of E prime is 1 minus P of E. The odds favor A occurring is A to B. Is A to B. You know, I could write A to B as A over B. It's easier to handle when I use algebra. So, and by the definition, so that is a given. That's a given information. The odds is A to B. By the definition, the odds favor E, supposed to be P of E over P of E prime, right? Right? The odds favor E would be P of E over P of E prime. And we are going to write P of E prime as 1 minus P of E. And now we can equate this part with this part. Okay? Because they are both represent the odds favor E occurring. So now we make them equal. So we have P of E over 1 minus P of E equals A over B. And we are going to do a cross multiplication because this is a proportion. You don't have to know the detail. So you multiply those two together and then equate that with the multiplication of those two. Okay. Yeah, this is actually a challenging algebra problem. So we have A times 1 minus P of E, right? Top right, multiply with bottom left, and let that equal to bottom right times top left. Okay, and then we simplify the left side. Distribute. A times 1 is A minus A times P of E. B times P of E. And we are going to add A times P of E to each side. Cancel this. We have, they cancel, right? We have A on the left side by itself. On the right side, we have B P of E plus A P of E. Oops, I ran out of space. A P of E. And that is A equals, we factor P of E out, and we have A plus B inside the parentheses. And then we divide each side by P plus A plus B, sorry. We divide each side by A plus B. Cancel A plus B. We have A over A plus B on the left side. We have P of E on the right side. And this is the answer. This is an algebra problem, more like algebra problem. It does use the concept of odds, but the challenging part is the algebra. Well, I'm recording the class, so it would be necessary probably for you to watch this part a few more times, right? So P of E is A over A plus B. A over A plus B. And also is a multiple choice question. Since it's a multiple choice question, you can make sense of the other options. If other option doesn't make any sense, then you have to choose this one. We did this one. This is about why did we skip this problem? Oh, it's just use 1 to minus the probability. It's not something fancy. See number 21. Oh, this is about us. Let's do this problem. Okay, so odds is not probability. Even it somehow does describe the chance of or the likelihood of a certain result. Basically, it's compare with the chance of that result happening and the result not happening. But it uses probability. It is different from probability, but it uses probability. We are looking for the odds in most reduced form, means that you have to simplify, in favor of selecting selecting a member of the population with 4 years or more of college. Okay, let's do this one as the last problem today in the QR session. Let's firstly find the probability. Randomly select a person who has 4 year or more college. 4 year or more college. 4 year or more. Okay, right here. All right. So let's use A to represent that event or that result. P of A. Randomly select a person, and the person happen to have a 4 year or more college education, is going to be 42 over 165, right? I would purposely keep the same denominators. Even sometimes I might be able to reduce a certain fraction. I wouldn't do that. Purpose is to keep them have the same denominators. Then P of A prime would be 1 minus 42 over 165, which is 165 over 165 minus 42 over 165. And that gives 123 over 165, right? I keep the same denominator. So the odds favor A. Okay, the odds favor A would be P of A to P of A prime. P of A is 42 over 165. P of A prime is 123 over 165. So purposely keep them have the same denominators, have a benefit because we can just get rid of it. Then we have 42 to 123. Do the two numbers have a common factor? Yes. They have a common factor 3. So we're going to divide this number by 3, divide this number by 3, divide this number by 3. And we would have 42 divided by 3 is 14. Yeah. And 123 divided by 3 is going to be 41. Yeah. And that's simplified. Okay, that is simplified. I think 41 is a prime number. So the result is going to be 14 to 41. 14 to 41. Right? Okay, guys. Essential class, I'm going to see you in 10 minutes. We are going to continue working on MyLab Math. And the other section, I'll see you next Monday. Have a good weekend. Feel free to email me if you have any questions. All right, guys. Bye-bye. See you in 10 minutes. Yeah, very good. Bye-bye.